Have you ever just stopped and wondered what sound is? I mean, really think about it. It's everywhere, all the time, from a quiet whisper to a massive thunderclap. But what is it, fundamentally? How does it actually get from a source, like a guitar string, all the way to your ears?
Well, that's exactly what we're going to dive into today. We're going to uncover the secrets of sound, and we're going to follow its journey from a simple, totally invisible vibration all the way to becoming a powerful tool that lets us see inside the human body. Okay, so first things first, where does it all begin? What is the one single thing that has to happen for any sound to exist? Believe it or not, it all boils down to this one thing, a vibration. Yeah, that's it. Every single sound you've ever heard and every sound you ever will hear starts with this one simple physical action. It's the spark that kicks the whole process off. So what do we even mean by a vibration? It sounds technical, but it's really not. All it is an object moving back and forth really, really fast. You can just think of it as a super fast wiggle. And that little wiggle is the first step in the journey of every sound. And this isn't just some abstract idea. It's a real physical force. I mean, if you take a vibrating tuning fork and dip it in water, it'll splash water everywhere. Or it can literally knock a little ball away on contact. It's the same thing when you pluck a rubber band. You can actually see it vibrating. Heck, the sound of my voice reaching you right now is all starting from the tiny, rapid vibrations of my vocal cords. Okay, so we've got our spark, the vibration, but how does that wiggle get from its source, travel across a room, and actually get into your ear? This is where the journey gets really interesting. This part is so cool. The vibrating object bumps into the air particles right next to it, and then those particles bump into their neighbors, and so on, creating a chain reaction. But here's the key part. The air particles themselves don't fly across the room. They just pass the energy along before settling back where they started. It's exactly like doing the wave at a stadium, you know? People stand up and sit down, but the wave itself travels all the way around. So you can picture it like this. As the object moves forward, it squishes the air particles together into a little high-pressure bunch. That's called a compression. Then, as it moves backward, it leaves a little bit of empty, low-pressure space. We call that a rarefaction. And it's this constant push and pull, this series of compressions and rarefactions that travels outward as a wave. Now, this kind of wave has a fancy name, a longitudinal wave. But honestly, the best way to picture this is with a slinky. Imagine laying a slinky on the floor and pushing one end. You'll see that little bunch of compressed coils travel all the way down to the other side, right? The coils themselves just wiggle in place, but the energy travels. That is exactly how sound moves through the air. All right, so now we know how a sound is made and how it travels. But why do different sounds, sound different? Why does a high-pitched flute sound nothing like a deep bass drum? It all boils down to two key characteristics. And those two things are pitch and loudness. Pitch is simply how high or low a note sounds. Think a tiny chirp versus a big foghorn. And loudness is, it's exactly what you think it is. And what's amazing is that both of these qualities are tied directly to the physical properties of that sound wave we've been talking about. Pitch is all about frequency. And frequency is just a measurement of how many complete sound waves pass by a single point in 1 second. So if an object is vibrating really fast, it creates more waves per second. That means a higher frequency, which our brain interprets as a higher pitch. It's a direct one-to-one relationship. And as a bit of trivia, we measure frequency in a unit called Hertz, or Hertz for short. It's named after the German physicist Heinrich Rudolf Hertz, who did some incredible work with waves. So every time you see that unit, you're seeing a little nod to him. Okay, so what about loudness? That's determined by the wave's amplitude. You can just think of amplitude as the wave's power or its intensity. If you tap a drum lightly, you create a small vibration. That's a low amplitude wave, and it gives you a soft sound. But if you really slam that drum, you're putting in way more energy, creating a huge vibration, which results in a high amplitude wave and a much, much louder sound. Now, what happens when these sound waves don't just travel freely through the air, but they actually run into something? Well, that leads to some very familiar effects, and it also opens up a whole hidden world of sound we never knew was there. You know the most common example of this, of course, an echo. And an echo is nothing more than a reflected sound wave. The sound travels from you, hits a big, hard surface like a cliff or a building, and then bounces right back to your ears. It's just like light bouncing off a mirror. So, have you ever wondered why you can hear an echo in a big canyon but not in your bedroom? It's all about timing. Our brains need a tiny delay, about a tenth of a second, to be able to tell the difference between the original sound and the reflected one. And for that to happen, the sound has to travel a certain minimum distance and back. And that magic distance? It's about 17.2 meters. If you're any closer than that, the echo gets back too fast and your brain just mushes the two sounds together.
But here's where things get really wild. The entire range of sounds that humans can hear is just a tiny sliver of all the sound that's actually out there. Our hearing is pretty much limited to between 20 and 20,000 hertz. Below that, you have infrasound, these super low frequency rumbles that animals like elephants use to communicate over huge distances. And way above our range, there's ultrasound, which animals like bats and dolphins use as a kind of natural sonar to navigate and hunt. The world is literally filled with conversations we can't hear at all. So naturally, once we humans figured this out, we started finding incredible ways to put it to work, especially those sounds that are completely silent to us.
And that high-frequency ultrasound has been a total game changer. We use it for everything from cleaning tiny, delicate electronics with just vibrations to its most famous application, seeing inside things without ever having to cut them open. The principle is exactly the same as an echo. In medicine, high-frequency sound waves are sent into the body. They pass right through soft tissue, but they bounce back or echo when they hit something denser, like a bone, an organ, or a tumor. A computer then listens to all those tiny echoes and uses them to build a detailed picture. And the same idea is used in industry to find tiny invisible cracks in metal before they can cause a catastrophic failure.
So when you really stop to think about it, sound is so much more than what we hear. It all starts as a simple little wiggle in the air. And from that, we've created technology that lets us literally see the invisible. It really makes you wonder, doesn't it? If we can already do all that, what other secrets is sound just waiting to tell us?